when we have two solutions, to the Schrodinger equation, which are linearly independent. So let me say two linearly independent solutions. Dependent solutions to the Schrodinger equation, which belong to the same energy, E. We say that energy eigenvalue is degenerate. Okay, so here we have a case of degeneracy, right? Because the energy is the same, but we have two different linearly independent solutions. Okay? And degeneracies always arise from symmetry. Okay? There's something called accidental symmetry, degeneracy, but real degeneracies always arise from symmetry. Okay. Can you tell me what the symmetry is here?
It's a mirror symmetry.
Yeah, it's a symmetry. I would say, well, Nian is saying mirror symmetry, but what I would say is that it's a symmetry about the homogeneity of space. Space looks the same, going, well, I guess, yeah, left, so that's a right. If you in that direction and in that direction, space is the same, right? So that's what Nian is calling mirror symmetry. Okay. It's not important what symmetry what you call them, but that's what it is. So Schrodinger equation is a linear equation, right? So given these two solutions, I can now construct a solution which is a linear combination of these guys, right? Do you agree that this is also a solution where
Yes,
alpha and beta are complex constants, okay? Now, this solution, psi1, had a very clear physical interpretation. It represented a particle moving to the right. And this solution also had a very clear interpretation. It represented a quantum particle moving to the left. So what is the interpretation of this guy then?
It has some probability of moving to the right or the left.
Correct. Yes. Exactly. Well, is it like I mean, do you think it's a probability, like it's a classical probability in the sense that, oh, we just don't know. It's something that we just haven't.
It's in a superposition of both states until we measure it. Quantum probability.
Yeah, that is the language. Yes, that's exactly. So there are two ways of looking at this. One is, we might say, oh, this just represents the fact that we don't know enough of the system. Yeah, we just know that there's some probability it can go to the right and there's some probability it can go to the left. But, but this state is actually kind of a fictitious sort of, representation of that. That there is no way to actually, that the particle cannot actually be in such a state. It is either in this state or that state, and the alpha and beta are somehow telling us that we don't know, we don't have enough information, and therefore we are representing that as alpha and beta. Now that would be a wrong interpretation, okay? And at some point in the future, either in this course or in a future course, I will show you why. So the fact that the particle is in a linear superposition of these two, linear superposition is a linear algebraic term. It's a mathematical term where you take two vectors, psi1 and psi2, you're adding them, right? So mathematically, it has a meaning. So physically, what it means is that you can actually verify whether or not a particle is in a linear superposition. Okay, it's not something, maybe not in this case, but there are other cases where you can verify. Even in this case, there might be some clever way of doing it. I just haven't thought about it. Okay, so this is something quite bizarre, right? That a particle, because when we measure, we only measure particle, in a one-dimensional system, we can only measure a particle going to the right or left if it has some non-zero momentum, right? If it has a non-zero momentum, it must be going left or right when we measure it. But when we don't measure it, it can be in a superposition of states going left and right. This is the Schrodinger cat. This is Schrodinger cat state, okay? This is basically, and when we observe it, the particle collapses into either this state or this state. And that is the collapse that we discussed in the last lecture, okay? So let me just write down a few words, right? Psi represents a superposition of two states, when we say measure the momentum psi collapses to psi1 with probability alpha squared, or psi2 with probability beta squared. Okay. Now, what if I found a way to measure the energy of this particle without measuring the momentum? What do you think would happen to the state then?
It's 50-50, like lucky.
Right. So
I
you're
think it would
saying that?
also. I think it would also choose the state for the momentum as well.
Okay. So if I apply the Hamiltonian operator on this state psi, okay, psi is alpha psi1 plus beta psi2, right? So I can now write this as, this is a linear operator, right? So I can write this as, alpha h psi1 plus beta h psi2. Now, psi1 is an eigenstate of h, psi2 is also an eigenstate of h, right? So we can write this as ae psi1 plus beta e psi2. And we can factor out e, then I get alpha psi1 plus beta psi2 equals to e psi. So that means that the linear combination, is no longer a momentum eigenstate, right? Because this is, but it is still an eigenstate of the Hamiltonian, right?
Yes, sir.
Right? Because The fact that it's not a momentum eigenstate is verified that if you apply P on psi, you get alpha, alpha, say, square root of 2me psi 1 minus beta square root of 2me of psi 2. And if you factor this out, square root of 2me, inside the U bracket, you get alpha psi 1 minus beta psi 2, which is no longer the state psi 1, right? So this state is an eigenstate of the Hamiltonian operator, but it is not an eigenstate of the momentum operator. Okay? So if you were to find a way of observing the energy of the system without measuring its momentum whatsoever, then according to quantum mechanics, remember that if a particle was in an eigenstate of some observable psi, such that O of psi is O of psi, then if you make the observation, what is the result of the observation? You will just get O, right? And according to quantum mechanics, this state will continue to remain in that state. Okay? So according to quantum mechanics, if you were to find a way to observe the energy of the state, it actually will not collapse to psi 1 or psi 2. Okay? It's only when we decide to measure its momentum, it's going to collapse to either psi 1 and psi 2. Okay? So go back to the postulates of quantum mechanics and see if you can figure this out, if you can make this more clear, okay? Any questions? This is a very, very important but subtle fact.